Okay. Now we're good. I'm going to back this up just a little bit. Oh, please don't be fuzzy. Okay. We're going to talk about parametric relations and inverses today. Like I said, we're just going to focus on the parametric relations here to begin with. And I want you guys to consider a situation here for me. Let's say plane. Sketch out the path that an object is going to be moving at. Okay, it's not going to be a function. Okay, we're going to kind of not worry so much about functions for a minute, and just consider like if, let's say, looking down at an object that was just kind of moving around in some way. Maybe it was like an airplane, and I had an aerial view of this airplane from up top, and I could see the path that it was taking. Okay, or I was looking at like the path. If I was some kind of conservationist, and I was looking at, like, I was really interested in squirrels, and I was looking down. I had a camera set up, and I could see the path that the squirrels were running around in the park or something like that. Okay, so I'm just tracing out some kind of a path, some kind of an object, animal, whatever, is moving at. Okay, so it kind of starts here and swings around and kind of does something like that. So it started here and it went there. So maybe, like I said, like this is, you know, like the aerial view of like a park, and there's this little squirrel running around. And so I was like timing it and seeing where the squirrel was at any given time in the park. Okay, well, maybe we'll just stick with the squirrel example here. Okay, so so this point right here would be we call it the initial point, and this point over here maybe was the where the terminal point was. So there's a flow to this where it has a starting point and ending point, so it has to go in this direction. Okay, so the squirrel was moving in this kind of a direction towards the terminal point. Okay, and so what I did then, let's say, was I took this path that I had and I kind of gridded it out. So put it on a coordinate plane then and said, all right, so if I'm doing some measurements, let's say these are some measurements in feet. So it's kind of a small little area. So maybe this is 1 foot, 2 foot, 3 feet, 4 feet. So within this little 4-foot area, the squirrel scampered in a quick little circle like that. And then I'd have, you know, feet going this direction as well. So 1, 2, 3, 4, 5, 6. Okay. And so I got 3 pieces of information here then on my squirrel that I'm looking at. Number 1, its x coordinate. Okay. Because I can track anywhere on the curve. So let's say like the squirrel was right here in this little dip here. So what would be its x-coordinate in that little dip? Well, somewhere about 4.5 maybe. Okay. And then the second piece of information I have would be the y-coordinate of the squirrel at any place on the curve. So at that point, then the maybe it's like 2.8 or something is the y-coordinate for that particular point. And then the third piece of information that I have is time. Because I have the squirrel running in this arc. I know that's the path that it took. But I also know, because I've been timing it, where the squirrel was when along there. Okay? So my initial point would be like t equals 0, time equals 0. And then depending on how fast the squirrel was moving, I can give you any other time along there. Okay? So at the initial point, t equals 0. And then the terminal point, this would be just whenever time stops. So it depends on how long it took the squirrel to do its little scampering around there. Okay, so this idea of having 3 different things will allow us to create a set of equations that describes the path of this. Okay, so what we're going to have are two equations. One equation that has actually two functions. One is a function for x, and another function is a function for y, both of which are based off of time. We talked about function, we talked about input and output, right? In parametric equations, let's just talk about x first. My x equation, the input of the x equation is time. Okay, so if I were able to calculate an x equation for this little squirrel, then I would be able to tell you what its x coordinate was if you were able to tell me how much time had passed. You input the time, I give you the x coordinate. Okay? And same thing for y. I'd have a second equation for y. You tell me how much time has passed, I plug it in, I can tell you what the y coordinate of the squirrel is at that time. So there are two equations that describe one path because I have this third thing to work with, time. Time is my input for both, and then my outputs are x and y. So I can get ordered pairs. I can get an xy pair for any given point in time. So let's say after maybe 1 second, the squirrel is right here. So this would be our t equals 1 second position on the curve. Okay? And so at that point, if you kind of look at the scale, so I'll come out here. So at t equals 1, looks like x is approximately, what, about 5.5 maybe? And y is approximately, yeah, maybe like 2.8 or something. So if we think of them as these input-output equations where the input is time for each one, a way of describing this, you could say x of 1 equals 5.5 and y of 1 equals 2.8. Okay, the input is the t, the first one, x of t. So x of 1 is about 5.5. Y of 1 is about 2.8. Okay? So this is kind of the concept. This is what we're going to be doing with this. Now, we're not going to be looking at any paths that are quite this complex because based on the background math that we have, it's going to be difficult to come up with some parametric equations that truly trace that thing out. So the graphs we're going to have will look somewhat more normal. They'll look like shapes you're used to seeing and not do anything too terribly interesting at this point. But it's the first time you guys have seen this, so I don't want to get too complicated with that. But does this kind of make sense, though, as far as what it is? The input-output idea? I give you time. We get a position, an x and a y together. Okay, because that's what we're going to do next. We're going to take parametric equations. I'm going to give you the equations first, and then we're going to see if we can come up with some ordered pairs for it, and then start to kind of plot it out a little bit. Okay, so let's say I have x of t equals 2t plus 1. Okay, so that would be my equation for x using time. And then my y equation, maybe let's go 1 minus t squared. And then I always have to give a domain for t, okay? Like in this one, with the squirrel running around. Okay, time started at 0, and time ended at, I don't know, so whenever the time was stopped. So maybe in this case it took the squirrel 5 seconds to do that path. So my t would go from 0 to 5, okay? Well, if I'm going to give you two equations here, I got to give you where does t start, where does t end, so you know where to start and stop the little curve. So usually we start with 0. So let's say for t between 0 and maybe just 4, okay? And I don't have a context for this one, so I mean it would depend. t is time, so maybe time was in seconds, maybe it was in hours or minutes or whatever. To do what we need to do, it doesn't really matter. But if it was actually talking about something real, you'd have to have some kind of value or some kind of unit for that t that you're using. Okay, so we need to figure out what this curve looks like. We want to plot it out. Okay, so we need to come up with what are all the little ordered pairs, and then, like we normally do, plot the different ordered pairs and then connect the dots. Okay, but the trick is this time our input is time. Okay, so you guys have made XY charts before, right, in algebra when you're plotting points and you put it all together. So we're going to make, since we have three things, a TXY chart. It's going to have 3 columns to it. And t runs from 0 to 4, so we'll go up by 1. So 0, 1, 2, 3, and 4. So we'll plot 5 points here. All right, now making the rest of the chart's pretty straightforward. You know what t is for each different row, so you've got 2 equations to plug into, one for x, one for y. So you can use that then to quickly fill out the rest of the chart. So take a minute and do that. Okay? Start with x, plug all those numbers into the x equation, fill up that column, then go over to the y equation, do the same thing for that. Okay? I'm going to freeze this, and then I'll quickly put them in, and then I'll unfreeze it, and we can check and see if we got the same thing. Okay, so maybe I'm going a little too fast, but if you're done, you can check it out. That's what I got. All right, and each one of these rows is another ordered pair, right? An x and y that go together. So we've got some points that we can plot then. Go from 1 to 9, y between 1 and negative 15. So we just need to make sure that our coordinate plane that we draw matches that. So y, we're going really negative. X, we're going positive. So we're going to be in the 3rd quadrant here. Or 4th quadrant, sorry. Okay, so let's see what scale we need. For y, we got to get down to negative 15. So maybe, I guess, counting by 4s would work the best for what I've got here. So that would make this positive 4. And then the x, we just got to get up to 9. So I'm going to count by 2s. But however you want to set up your scale, as long as it makes sense that you can see everything, that's fine. So, all right, so let's just start plotting these points. We got 1, 1, so 1, 1 is about right there. 3, 0, be here. 5, negative 3, about there. 7, negative 8. And 9, negative 15 would be about right there. Okay, and then just connect up the dots. Now be careful though. Don't go beyond the initial and terminal points though. Okay, it doesn't keep going. It starts and it stops. So it's this curve, but just like that. Okay, here's your initial point. Okay, that's when time was equal to 0. And here's your terminal point that's when time is equal to 4. Okay, now having the information that we have now, we've got a graph of a function, which we could have gotten without parametric equations, but we have the additional information now, too, about time. Okay, so where was this object when time was equal to 1? Well, I can go over to my chart. It was at 3, 0. And I can even label that right on the graph if I want. So kind of in the last point, you can go through and just start kind of entering in that information too. That's where t was equal to 1. Here's when t was equal to 2. Here's when t was equal to 3. Okay? So you've got a very detailed look at the path of this object. Okay? Where it was, when it was, is all on the same graph together. Okay? That's what parametric equations do. Okay? They allow you to see the path of the object and include the time with it as well. Okay? That's the idea with that. So the other thing that we will do with parametric equations is, let's say I want to know what the equation of the curve is, just using x and y. Okay? So yeah, this is great. I've got the time and all that on there. Oh, just what is the equation of this curve? Y equals what? What would that be? So we can do a little bit of algebra to help combine those together. Okay? So when I'm done, I'm going to have an equation using x and y, but what's going to be eliminated then? T. So I want to take these two equations that I have up here, put them together somehow, but eliminate t. How might I do that? How can you combine two equations together by eliminating a variable? Yeah. Nope, we actually don't need the inverses here. That's going to come up later, though. That is related to this, though. Yeah. Yeah, there's going to be a way that we're going to have to make them equal to one another so that we can then, put them equal and then get rid of t. So let's think about that process for a minute. I'm going to come down here, the notation for right now, and just take a look at these two equations. X equals 2t plus 1, and y equals 1 minus t squared. Now, whether we're making them equal to one another, which there is a way to do that, and it's a valid way to do it, but sometimes it creates a little more work, or not, really the crux of the matter is it's going to involve a substitution of some sort. You eliminate variables when you substitute in for one, because as soon as that substitution happens, that new piece comes in, that old variable that was there is now gone, right? So we want to get rid of t, okay? So let's do this. Take the x equation. Solve it for t. It's going to be a couple steps, but I bet you can do it in your head. So what is that? What is t equal to if you solve that first equation? It's going to be what? Still going to have x in it, though. Yeah.
Negative x plus 1 divided by 2.
You're close. X minus 1 divided by 2. You got to subtract the 1 over and then divide by 2. So it would look like that. Okay. So, anybody see the substitution I need to make now? If t is equal to x minus 1 over 2, take a look at the y equation. What does the y equation have in it as its variable? T. So what can I do? Take that t that's in that second equation and make it what? Right. Just make it the x minus 1 over 2. Okay. So we're doing a kind of a composition of functions here like we were doing yesterday. But basically it's just a substitution. So t equals that. So replace t with what it's equal to. So y equals 1 minus x minus 1 over 2 squared. Okay? So, if we were to graph this, which we are in just a minute, we're going to do it on a calculator. So if we look at this graph, this right here should be a piece of this. Does that make sense? Because this has no restriction on where it starts and stops, right? It's just going to keep going. But this right here has a particular starting point and ending point, but this little piece here should be a part of this entire curve, okay? So take a look. Graph it on your calculator. Make your window the same as this, okay? The same as the graph we produced, okay? Change that window up to make it look the same, and then take a look at that graph. It should go right over where those points are that we just plotted. I will do the same. All right, so 1 minus. And be careful about how you plot these, or how you type it in, because it can be a little bit tricky with the parentheses. So should look like that. It's 1 minus x minus 1 in parentheses over 2, and then that whole thing in parentheses squared. That's what it is. All right, and then make sure your window matches. Our x's went we'll go 0 to 10 maybe, just to make it a little bigger. And our y's, we were all the way down to negative 15, so maybe I'll go negative like 16, and then the max, I don't know, maybe like 2 or something. All right, so let's see if we got the same shape as this guy here. So, same thing, right? So what we've done is we've come up with the equation for the curve that our little object was traveling along, but like I said, it's the entire curve. It's not just that little piece of it that parametric equation is measuring. Okay. So I think that is where I'm going to stop today, actually. I'm going to give you guys a little bit of time to hang out here. The next thing I'm going to jump into is inverses, and I'd rather just do that all on the same day, so we're not breaking it up. So we will stop. All right. I think we're ready to go here. So, okay, so today we're going to get into, like I said, inverses of functions. You guys did talk a bit about this in Algebra 2, so I'm just curious, anybody remember anything about what an inverse is? Yes?
Don't you switch the x and y? Solve for x?
Solve for y. Yeah, so you would, so if you have some kind of an equation, like let's say y equals 2x plus 3, the inverse of that would be x and y switching roles. Okay, so the x becomes y and the y becomes x. So the inverse would be x equals 2y plus 3. Okay, now usually we want to write these as a function. Okay, so the only reason that we would solve for y is if we're interested in the inverse function. The inverse relation is actually right there, and we could just leave it, and it's fine. It just shows, a relation is just showing a relationship between x and y, which this equation does, right? Shows a relationship between them. It shows how one's equal to the other, but it's not a function, okay? So if a relation is a function, we should be able to solve it for y and then write it in function notation. So if that was my goal, the inverse function, okay, then I would take that, solve it for y. So I would have, let's see, y equals, I have to subtract 3 divided by 2, so x minus 3 divided by 2. Okay, but this relationship here is really the same as this one. I've just, moved things around using algebra. Okay, but what I've done here, though, is because I can solve it for y, I've proven that that original equation that I wrote down, this original function, because it's solved for y, does have an inverse that is a function. And that's not always the case, though. Okay? So if we start taking a look at some other functions, sometimes we're going to run into problems when we try to do this process, try to find the inverse. So, and I'll write this one in function notation to begin with even. So let's say I've got f of x equals x squared plus 3. Okay, and I would like to see if the inverse relation to this is indeed a function or not. So, to actually go through the process of doing that, remember f of x is really just a fancy way of writing y if it is a function. So what I would usually do is just take this thing and then change it into this, y equals x squared plus 3, and then do what we just did with the last one. To do the inverse, x and y switch roles. So we just change them. Oops. So my inverse then is x equals y squared plus 3. So that is the, like we said before, the inverse relation. Okay? So if we want to check to see if it's a function, we got to try and solve this thing for y. Okay? So first step, I would subtract 3. X minus 3 equals y squared. And then what? What would be the last step to solving this? Square root. Now, we've got to be careful though. If I use a square root to solve an equation, I technically have to use what? Plus or minus the square root. Yeah. So what I have here then, and I'll just switch the y onto the other side, but it's plus or minus the square root of x minus 3. Is that a function?
Well, no, I
Or
was going to say, wouldn't you have to also be plus or minus y?
No, you don't. Because it would just kind of cancel out, technically. Because you would have plus or minus the square root of y squared. But if you had a plus or minus equals a plus or minus, it's kind of a long story, but you could divide by negative 1 on either side to get rid of the minus, and then divide by positive 1 on either side to get rid of the plus, and you'd end up with still a plus or minus on the other side. It's kind of confusing, but I can explain it more later if you want. But yeah, technically, just long story short, you don't need to do it. Just on one side of it, and it's fine. So I guess as well here then. Is that a function? It's plus or minus the square root of x minus 3. Remember, a function, for every one input, you have one output. Does this have one output? You'd end up with two answers, right? You got to use the plus and you got to use the minus. There's two. You get two answers for every one input. Okay? So this is not a function. So this original function, it has an inverse, but the inverse is not a function itself. Okay? So basically what this is telling us is inverse is not okay. So we're going to switch gears here just a little bit, and we're going to go and look at inverses from the graphical side of things. Okay, so this is kind of the way of going about it. Okay, if you have a function or if you have an equation you want its inverse, you just switch x and y and solve and all that. How does it work on a graph? Well, there's a relationship between the two, the original function and its inverse when you put it on a graph. All right, so let's just take some ordered pairs to begin with, and let's see if you guys can use that to either discover or remember what the relationship is on a graph, okay? So I'm going to do my original function, or my original relationship, I guess, because it's not necessarily going to be a function. But I'm going to do one in one color and the other in another color and see if you can pick out what's going on here. All right, so let's start with so say we've got 2, 2 is A, 2, negative 3 is B, 1, 0 is C, and negative 2, negative 3 is D, and maybe one more. Negative 1, 2 is E. Okay, so somebody remind me here again. What do you do when you make an inverse? What were we doing with the equations when we did that inverse step? You switched x and y. Okay, so if I have a bunch of ordered pairs and I want their inverses, what am I going to do to them? Okay, so you're one step ahead of me. So we're going to switch x and y, and then we're going to see that, what you just said. Okay, so if we, for each one of them, think about what the coordinates are, okay, and we're just going to swap them then, okay? So what are the coordinates of A? 2, 2. So if I swap x and y, what are the coordinates of its inverse? Still 2, 2, right? So the inverse of A is in the same spot. So it's kind of right on top of itself. And we're going to put little primes for each of the inverses. So we'll say that, so there's A prime, there's the inverse of A. Okay, what about B? We're at 2, negative 3. So what should be the inverse of that? Negative 3, 2. Okay. So negative 3 up 2. And that's going to be B prime. Oh, I totally screwed up my scale over here. Did anybody else catch that? Yeah, sorry. We'll assume there's a negative 1 in there somewhere. C, we got 1, 0, so the inverse should be 0, 1. So that's going to be here. D was, let's see, negative 3, negative 2, so that's going to be negative 2, negative 3. So that's going to be down here. And then E, we had negative 1, 2, so that's going to be 2, negative 1. So 2, negative 1, I guess, will be somewhere like right there then. Okay, so maybe it's not clear by looking at that right now. This line right here. Okay, each of those points is a reflection, except for like this D prime because I screwed up my scale, but you just ignore that one. The rest of them look pretty good though. Each one you can see is just a direct line, okay, because the X's and the Y's are changing. So the A, it makes sense, it's right on top because that lands right on that line of reflection. C is reflected over it. E is reflected over it. B is reflected over it, okay? So with functions, remember a function or our graph of an equation, it's just a big clump of points, right? So you're going to do this same kind of process. You're going to do these same reflections, but you're not just going to do one point at a time. You're going to do the entire thing, the entire curve, whatever it is, okay? And sometimes that's easy, and sometimes that's not so easy, okay? So let's try that, okay? I'm not even going to give you an equation here. Let's just see if we can kind of visualize how this inverse should look. So if this is our original function, so, well, I won't label it. I'll just leave it like that. Okay, so the inverse needs to be a reflection of that over that dotted line. Okay? So can you visualize that in your head? Right, that's where I'm going with this one. Yep. So that inverse, it should be another parabola like this one, except it's going to do like this, right? It's going to wrap around. So it's a parabola that opens to the right, not a parabola that opens up and down anymore. So it kind of come around like that. All right, and what Josh just said was the inverse is not a function. Okay, this is how we can see it on the graph, right? What is that test that we use to tell if something is a function or not on a graph? Yeah, vertical line test, right? So we can take a look at this inverse that we've just created, and we particular one would not be a function when we did it. Okay. Graph that I put on there, what does it look like? What of your 12 basic functions does it look like I just created there? Squaring function, okay? So let's assume that that's what it was. If the original function was f of x equals x squared, basically like we did earlier, y equals x squared, so the inverse is x equals y squared, square root both sides, so y equals plus or minus the square root of x. So is y equals plus or minus the square root of x a function? No. Okay? So I know that what I'm getting should not be a function. And in fact, what I'm seeing here is two functions. You're seeing the square root. Think about the shape of the square root from your 12 basic functions. This should make a bit of sense. The square root, do you see it there? It's the top red parabola. Okay? And then the bottom of it is the negative square root of x. It's the same thing as the square root of x. It's just been reflected down. Okay? So this red curve is actually the collection of two functions put together. All right? And that's the inverse. Okay? So here's a question for you then. How could I, without graphing the inverse, just look at the original function and be able to tell if it's going to be a function or not when it's the inverse? Yeah. Okay, yeah, all the examples I've done so far have been square roots, but that's not the only thing. But that's true. If you go through the process of finding the inverse and you end up with a square root as part of your solving it, it's going to be not a function. But just look at the graph itself. What feature about how it's made, and remember what I just talked about, the vertical line test tells you if something's a function. So what about the original would do that? Yeah. You're absolutely right. Yep. On the original function, if you do the horizontal line test, we'll tell you if the inverse is a function or not. Remember, x becomes y, y becomes x, right? With inverses, everything switches. So the vertical line test on the inverse becomes the horizontal line test on the original function, right? Okay? So if I just graph you something, you should be able to tell me right away. So that's I'm going to give you guys several functions to take a look at, or not necessarily functions, but several graphs, and just tell me, is the inverse going to be a function or not? Okay? Come on. Okay, so take a minute, and for each one, yes or no, and why. Is the inverse a function? Maybe I should write that at the top here. Okay, so let's real quick go through this. Just calling some random folks here. So let's do, Madison. First one. Is the inverse of that going to be a function? No. No, and why not?
Because you can draw horizontal lines.
Right. So if I put a horizontal line through this, I can find where it will hit more than once. So this one, definitely no. Okay, how about second one?
Yes, it is a function.
Mm-hmm. Yeah, so it's a because it passes the test, but it also passes the horizontal line test. So that inverse will be a function. Yep. Okay, next one, let's go for it. Is that going to be a function?
No.
Okay, why not? Correct. And not only that, what else is wrong with this one? It's not even a function to begin with, right? Okay, so yeah, definitely a no. The last one, angel, is that going to be a function when we do its inverse? Well, does it pass on a line test? No, it doesn't. So I put a horizontal line through this one. I can get it to hit more than once. So will the inverse be a function? No. Okay. So value functions, in general, that's what this one is, are not going to have inverses that are functions. So just kind of a little vocabulary here for you. So if a passes the horizontal line test, we call it 1-to-1. Okay, and that's some terminology your textbook's going to use. 1-to-1 means 1x to 1y, and 1y to 1x. Okay. For every one input. Well, if a function is 1-to-1, it takes that a step further. It says not only is there one output for one input, there's also there is one input for every one. It goes both ways. It's a two-way street then for those. Okay, so 1-to-1 functions on a line test. Their inverses have functions, or are functions, and all of that. Okay, it's all kind of wrapped up into the same thing. Real quick too, I just wanted to show you some notation before we move on. If you have that has an inverse, so maybe something like, say we got natural log x plus 2. I wanted to get to a different kind here too, so you weren't just seeing the same types every time. So natural log of x plus 2. This function is 1-to-1. Okay, I'll just let you know. It will pass on a line test. If you think in your head to what the basic function natural log x looks like, if you've got those graphs in your head yet, I don't know. But if you do, if you can visualize it, it is definitely 1-to-1, right? Okay, it passes the horizontal line test. So the inverse of this real quick. Y equals natural log x. So I do my inverse steps. Now it's x equals the natural log of y. I'm just going to just solve this thing out the rest of the way. So x minus 2 equals the natural log of y. So y equals, to undo this, I'd have to e both sides. Okay, so a little review there real quick about changing logs to exponentials and vice versa. We'll do more of that later, but that's how you would switch that one up. So now it's an inverse. It's not an inverse. It's an inverse. To show it's an inverse, you have a special connotation for that. So you do f to the negative first power. You're not actually raising it to the negative first power. Just notation for it. Okay, so if the original function is natural log x plus 2, then the inverse of f of x is e to the x minus 2. Okay, that would show this down here is the inverse function of this function up here. Okay, using that notation. That's how you would identify that. Okay, just wanted to show. Stuff relate to the parametrics that we were talking about yesterday. Okay. Well, inverses talk about taking x and y and switching their roles. Okay. In equations, we had two equations. So if I had a pair of parametric equations and I wanted to find an inverse, could not be easier. Okay. If I can find my pencil, I can show you that. Oh, here we go. So, real quick, let's talk parametric inverses. So let's say I've got a t equals t squared plus 1 or something. I of t equals maybe the square root of t plus 4. And let's say I don't know what's the inverse of that pair of parametric equations. And you might go, oh, crap, I got to do all that inverse stuff they just talked about. And some will apply to stuff with t. This is going to be confusing. It's not. Think about what you do when you take an inverse. You swap x and y, right? Okay. So if this is the original set of parametric equations, the inverse, what do you suppose x of t is? Yeah. It becomes y was equal to square root of t plus 4. And what do you suppose y of t is? T squared plus 1. It's super easy. Done. Okay. And I'm going to have jumping on your calculators here too so we can kind of take a look at this. Okay, your calculator can plot parametrically. I'll show you how to do that. And then because of that, we'll be able to take a look at a graph from equations and its inverse at the same time. Okay? So, what I'd like you to do first here is go into mode. Fourth row down is your kind of graphing mode that you have. There's which is what you're used to. It's always the y equals and you type something in. But there's 3 others, and we're going to explore 2 of the other 3 at some point during the year here. Parametric is the par. Pole is polar, which we'll do in the B section of this class. And this one we won't get to, but in calculus we do it a little bit. It's called sequential mode. That's if you're doing like C, you'll learn about later. So anyway, if you come down here, let's switch it to par. Okay, and then just exit out of that. And now go to y equals. Notice how it's changed. Instead of just y equals something, you have x of t and y of t. You got to put two equations in. Okay, so what I just did in class. All right, just see what it looks like. So we had t squared plus 1 got that t by the variable button still. I want to show you something here. I'm going to zoom way in on this. Take a look at this button. If you've ever been confused about this button before, don't be anymore. Has everybody been using this for x whenever you type stuff in? Okay. Take a look. It adds t, theta, n. What do you suppose each one of those are? They're variables for the different modes. This is function. This is parametric. This is polar. This is sequential. So every time we press this button, now that we're in, it's going to do a t instead of an x. Okay, it just automatically does that. So it's kind of a neat little thing there. Anyway, so we're in here now. So let's get the other part. It was what? Square root of t plus. Okay. Before you go look at the graph, we got to set up the window too. And the window's a little different. Okay. Notice it says t min, t max, t step. Well, when we were in parallel mode, we had to have a point and a stopping point, right? For the path we were traveling. Okay, so we got to tell it what's the t value you want to start with, usually 0, and then where do you want to stop it. So to something that should be sufficient. Yeah. Yeah. Okay. Step. Okay. The thing is going to play a game of connected when it makes this. It's going to plot the points along this curve and then connect all of them together. Okay. So the t-step tells the calculator to recalculate a new point. Okay. Does it want to? Should you just have it do t equals 0, 1, 2, 3, 4, and 5, and then connect those together, or right at it at point 1? So it's going to plug in a 0. It's going to plug in a point 1, point 2, point 3, point 4, point 5, all the way up to 5. And then take all those points and connect them together. So the smaller your t-step, the more smooth a curve you're going to have when you're done. It's going to look more accurate the smaller that number is. Now, caution. If you make this number too small, your calculator is going to sit here and kind of choke on it. Okay? It'll take a really long time for it to graph. Okay? 0.1 I have found, at least in general, tends to be a kind of a happy medium. Or 0.01 isn't terrible either. But if you make it like just 1, it's going to look real jagged and not look real accurate. But you want somewhere in the middle where you're not going to have to wait a half to plot it, but at the same time, it actually looks pretty good when you're done. So we're going to go with that. And this one, we're going to have to some 25 for the y mins and the y maxes. So let's switch those up. Okay, we can keep the scale at 1. Okay, so switch those up too. We want to be able to see the whole thing. And once that, now the graph, okay? Okay, so there it is. It's this really flat, skinny thing that comes out. So if it's inverse at the same time, super simple. Go down to the side here and swap them. Okay, so square root of t plus 4 for the x, and t squared plus 1 for the y. And so when I graph this thing, it should look like the reflection of the other one we just did, right? So let's take a look. And lo and behold, it is. Okay, and that works for any set of parametric equations. If you're looking for an inverse, you can do that on the calculator and look and see what the graphs look like. Yeah?
Mine's just not graphing.
Window range. Oh, it's because your y max is -25. That should work now. Yep. play around with this a little bit, experiment with some other ones that are maybe a little more interesting looking. That's fine. I think that would be good. But to kind of show you how you can do that. To work here on your homework then.